Hi, I'm Qianli. I'm presenting to you POP, our expressive shape modeling and scan animation technique that shows the power of point clouds for modeling 3D humans in clothing. Animatable clothed human avatars will play an important role in the digital world. However, currently still requires expert knowledge to design avatars with clothing that moves naturally on the body. The process would be simpler if we could automatically turn existing static 3D scans of people into animatable avatars. Achieving this requires a model for clothed humans that can produce pose-dependent clothing deformation and can generalize to previously unseen outfit types and styles. Unfortunately, most existing models are subject and outfit specific. The problem with current methods and the key to a solution lies in the 3D shape representation. 3D meshes are fast to render and compatible with graphics tools, but they rely on predefined templates with fixed topology, limiting their generalization to new outfits. Implicit surface models can represent arbitrary topology, but they are not readily compatible with animation tools, and rendering them is typically slow. Surface patch models are topologically flexible and offer fast inference, but lack representation power and can suffer from patchy artifacts. In this work, we introduce a new representation for clothed humans based on an old yet powerful representation, point clouds. Here we show how to use machine learning to make point clouds a powerful representation for modeling 3D deformable shape. Our model, named POP, meets all the requirements above. POP represents a closed human with a dense point cloud consisting of more than 50,000 points. The points are coherently positioned in space, resulting in a smooth global shape and detailed local geometry. The points have not fixed topology, enabling generalization to different clothing types. Surface normals are also modeled so that the point set can be easily turned into a mesh. This is achieved by a carefully designed neural architecture that models a clothing deformation field from the underlying human body using fine-grained local features. In prior work, the mapping from the body surface to the clothing surface relies on relatively coarse features that are shared either by the entire point set or a neighborhood of points. This leads to either a lack of details or patch-like artifacts. In contrast, we decode each point from its unique local feature. The continuous local point features result in a more coherent overall shape and improved local details compared to prior work. Using this dense point cloud representation, we build a system that models pose-dependent clothing deformation across multiple subjects wearing different types of clothing using a single model. To do so, we decompose the points feature into separate pose and geometry features. By using a separate geometric feature tensor for each outfit, our model can do cross-outfit modeling with a single shared decoder. To show the representation power of our method, we compare it with state-of-the-art closed human modeling methods by testing trained models on unseen poses. NASA uses an implicit surface representation and supports varied topology, but often suffers from non-smooth transitions between body parts. Scale produces a point cloud structured into patches. It also supports varied topology, but the patches are typically isolated from each other, leading to poor visual and mesh reconstruction quality. Note that both baselines need to train a separate model for each outfit. In contrast, our approach learns a unified model for multiple outfit types and generalizes well to unseen poses. It outperforms the baselines on every outfit type, showing a smoother overall shape, better local details, and a salient influence of body pose on the garment shape. We also find that multi-garment training is beneficial for leveraging common knowledge across garment types. Please refer to the paper for details. The trained POP model can also generalize to previously unseen outfits. We fit the model to a single scan of a previously unseen subject and outfit. This optimization gives a garment geometry feature tensor for the scan. POP is then able to animate the fitted scan with natural pose-dependent clothing deformations. Here, we show the results of a very challenging test. We trained POP with synthetic simulated clothing data, and we tested it by fitting it to a real scan of a person. Once fit, POP can animate the scan with plausible clothing deformations. In summary, we introduced POP, a dense point cloud representation and cross-outfit modeling technique for pose-dependent shapes of humans in clothing. POP is fast, expressive, represents multiple garments with a single model, and generalizes to both new poses and new garment shapes. POP also provides a new perspective on an old representation and shows how point clouds can model high-quality clothed 3D humans in motion. It not only serves as a state-of-the-art technique for modeling clothed humans, but also offers a solution to create animatable avatars from a single static scan. The code is available for future research of closed human analysis and synthesis. Please visit our project website for more information. Thank you.